Thanks for attending today's webinar. My name is Chris Murphy. I'm an applications engineer with Analog Devices focusing on condition-based monitoring. Today I'm going to talk about sensors to machine learning. Today I'll discuss why CbM is important, what sensors we can use to detect faults. We'll look at the condition-based monitoring precision data acquisition signal chain for MEMS and for piezo's, as well as some reference designs and platforms that showcase Analog Devices' wide range of CbM specific solutions. So what is CbM and why is it important? Condition-based monitoring involves monitoring of machines or assets using sensors to measure the current state of health. Predictive maintenance, or PDM, involves a combination of techniques such as CbM, machine learning, and analytics to predict upcoming machine or asset failures. According to a Wall Street Journal post, unplanned downtime costs industrial manufacturers an estimated $50 billion annually. Using predictive maintenance to limit this cost is critical in highly competitive manufacturing industries. Unplanned downtime in just one machine in a just-in-time manufacturing environment can cause delays that lead to unhappy customers, possible loss of those customers to a competitor, and a direct hit to a company's profits. So what are the advantages of a predictive maintenance system? A lot of industrial motors are designed to work up to 20 years in continuous production applications where they perform a critical role in keeping production online. A lot of these motors do not reach their projected lifetime. PDM enables maintenance teams to schedule repairs and avoid unplanned downtime. In some cases, up to 50% reported. And this leads to increased productivity. Early prediction of machine faults through PDM can also help maintenance engineers to identify and repair motors running inefficiently. For example, a cutting machine with excess vibration could lead to poor quality products. Identifying this leads to increased performance and product quality, which further increases productivity through less scrapped parts. Early prediction of machine faults can also lead to increased asset availability and lifetime by reducing unnecessary wear and tear on mechanical elements. With better diagnostic insights from predictive maintenance, more targeted maintenance can be carried out, leading to better efficiency and lower maintenance costs. Inherent in this early fault detection is the reduction in risk of a catastrophic failure where infrastructure or people could be damaged or injured. CbM and PDM are vitally important to Industry 4.0 and ensuring production is as efficient and reliable as possible. So we know CbM enables us to detect faults. Let's take bearing issues as an example of a motor fault. In order to minimize production downtime, it's imperative to know about the potential failures within the motor in order to be ready to deal with them. Bearings are a key failure element in the vast majority of industrial rotating machinery, as shown on this slide. And what this tells us is that any CbM system intended for use on rotating machinery should focus on bearing analysis as an early indicator of potential faults. This slide shows a simulation of a faulty bearing in a critical asset and the corresponding FFTs or Fourier transforms of the fault signature over time as the fault worsens. Bearing faults first appear at high frequencies with a very low amplitude. For predictive maintenance, measurements are made up to 10 kHz and beyond because that's where the vibration components of interest first appear. Now we need the highest performance sensors for predictive maintenance, denoted here in green, where we can detect the bearing fault at the earliest possible time. Over time, as the fault worsens, the fault frequency modulates down to lower frequencies around 5 kHz or less. And we can also see an increase in magnitude of the fault and also of the noise floor. Medium performance vibration sensors can detect these faults, shown here in orange. Medium because these sensors are not capable of detecting faults at the earliest point in time due to having smaller bandwidths and higher noise. And these sensors, for those reasons, are likely to be deployed on less mission critical assets. At this point in time, the fault has worsened, so it may also be possible to detect increased bearing temperatures or particles due to excess wear through oil or lubrication analysis. When the defect frequency approaches the natural frequency of the motor at less than 1 kHz, the magnitude has increased significantly. The noise floor also increases. Low performance sensors can be used for detection here, as noise and bandwidth requirements fit those of general purpose accelerometers. But it should be noted that motor failure is much closer, perhaps even imminent, if you wait this long. The easiest machines in terms of bearing fault detection, shown here as level 1, are those where sensors can be mounted directly on the bearing housing and where there's little vibration from other machine components. At level 2, we see more vibrations from other machine parts, so we need a sensor with a better signal to noise ratio or better noise performance. At level 4, for example with industrial gearboxes, sensors can no longer be placed directly on the bearing housing, but they can be placed on the transmission path from the internal bearings to the housing. And from this point on, as machines get larger, there's a requirement to have a higher G range. Faults like imbalance and bearing issues can generate significant vibrations. The best predictive maintenance strategy is one that efficiently utilizes as many techniques and sensors as possible to detect faults early and to a high degree of confidence. With that in mind, there is no one sensor fits all solution. So let's look at what sensors are commonly used in CbM and PDM applications. Magnetic field sensors such as Hall, magnetometer and search coils are typically low cost, small and stable over temperature. And magnetometers quite often will have integrated temperature sensors to help with calibration. These sensors can be used to detect faults, electrical faults such as rotor bar and end ring issues. Current sensors like current transformers are non-invasive and they're usually measured at the motor supply, even in the motor control cabinet. And this is known as motor current signature analysis. And this can be used to detect electrical faults like eccentric rotors, winding issues, rotor bar issues, power supply issues, and even mechanical faults such as bearing or gearbox failures. Lubrication quality can be detected with an inline particle monitor, which checks the lubrication oil viscosity and for contamination such as particles from excess wear. High-end temperature sensors such as infrared thermography sensors are expensive but highly accurate. Multiple assets or multiple sources of heat can be monitored at one time. Lower performance temperature sensors such as RTDs, thermocouples and digital temperature sensors are low cost, small and still considerably accurate. Changes in temperature are typically caused by excess friction, load changes, excessive starting and stopping of the asset or even insufficient power supply. Microphones are low cost, they consume very low power and are quite small, which makes them ideal for use in wireless CbM applications. Ultrasonic microphones can detect fault vibrations up to 100 kHz, which is very useful for detecting faults such as pressure leaks, even bearing condition, gear meshing, pump cavitation and so on. Accelerometers, in specific MEMS accelerometers, are low cost, low power, easy to install, which makes them ideal again for use in wireless CbM applications. Piezo accelerometers are more expensive, but they do offer lower noise and wider bandwidths, in some cases up to 30 kHz and beyond when compared to MEMS accelerometers. But both accelerometer types can detect bearing condition, gear meshing, pump cavitation, misalignment, load condition, and so on. So now we look at some vibration sensors for early fault detection. So here I'm comparing MEMS accelerometers and MEMS microphones to piezo accelerometers. And I'll just note, MEMS microphones are not strictly vibration sensors, but for comparison purposes, they actually fit into this comparison quite well. So data in each column is representative of the minimum or maximum variation within that category and doesn't correlate to adjacent columns. We can see piezo are the highest cost sensor, but they have the best noise performance. The bandwidth is also excellent, up to 30 kHz and beyond, but piezo don't have any integrated features, and power consumption is not ideal for wireless CbM installations, even though some parts have consumption down around 200 microamps. MEMS accelerometers for predictive maintenance, as you would expect, are more expensive than general purpose accelerometers. And part of this is because making low noise wide bandwidth accelerometers is tremendously difficult. And we can see with MEMS accelerometers, the bandwidth is ideal for predictive maintenance applications, although not as high as piezo. MEMS accelerometers are the only sensor with a DC response, which is very useful for slow rotating machines and also detecting tilt. They're also the only sensor with a self-test feature, which can verify if the sensor is still functional once deployed. And this could be very advantageous for safety critical applications. MEMS microphones can detect from tens of hertz up to 100 kilohertz in the case of ultrasonic at a very low cost. MEMS microphones along with MEMS accelerometers are ideal for wireless CbM systems. Accelerometers are the most commonly used vibration sensor, and vibration analysis is the most commonly employed predictive maintenance technique. It's possible to completely seal MEMS accelerometers hermetically in ceramic packages and piezo accelerometers in mechanical packages for use in harsh, dirty environments. This table focuses on physical, mechanical and environmental performance of the sensors. And this is where the key differences can be seen between each sensor, such as integration, tolerance to harsh environments, mechanical performance and attachment to an asset. Piezo accelerometers have industry standard interfaces like IEPE and 4 to 20 milliamp. The sensors are packaged in a mechanical module that can withstand vibrations and shocks without affecting performance and can be mounted or connected to industrial machinery with relative ease. They also have excellent performance in harsh operating environments. Jumping to microphones, in benign environments, MEMS microphones offer excellent performance for predictive maintenance applications. But currently there's a lack of information available on mounting MEMS microphones in harsh operating industrial environments with excessive vibrations or dirt or humidity. MEMS microphones have shown distortion of up to 8 dB when exposed to increased humidity for prolonged periods. Analog devices have pioneered MEMS accelerometers for use in predictive maintenance applications and continue to deliver industry firsts, namely MEMS accelerometers in mechanical packages or on mounting modules where the frequency response of the sensor is maintained when mechanically attached to an asset. Also MEMS sensors with industrial interfaces like IEPE and 4 to 20 milliamp capable of being retrofitted into a piezo mechanical module. And MEMS accelerometer performance and stability in harsh environments is also excellent, just like piezo. Here we can see a table of machine faults and sensor requirements to detect those faults. If we look at the first two on balance and misalignment, these can be detected with lower performance sensors. Fault signatures appear at lower frequencies, down to 1 kHz and below, and higher magnitude, so a low bandwidth higher noise sensor can be used up to 1 mg per root hertz. If we look at bearings and gears, we need high performance sensors to detect these faults early. We need a noise density of less than 100 microGs per root hertz and a bandwidth greater than 5 kHz, or even higher depending on the asset. And this is where piezo has dominated for years, but MEMS has now started to reach those performance levels. Now, making a wide bandwidth, low noise MEMS accelerometer is not easy. At the moment, analog devices are the only MEMS manufacturer to produce accelerometers that can compete with piezo sensors, the gold standard vibration sensor used for decades on the most critical assets. A recent report from Markets and Markets estimated that global demand for vibration monitoring systems will reach nearly 1.5 billion by 2020. This growth has been driven in part by the relatively low cost yet high performance of MEMS accelerometers, as well as their ultra low power enabling wireless CbM and PDM systems. And this looks set to continue. So this table shows a wide range of accelerometers in terms of performance and capabilities for predictive maintenance, from a simple 3-axis analog output accelerometer on the left to an intelligent edge node module for semi-autonomous PDM on the right. High performance sensors are highlighted in green, were designed specifically for predictive maintenance applications, and these can compete with piezo sensors. All other sensors highlighted in orange are targeted at high performance automotive or industrial applications like tilt sensing, for example, but are still highly suitable for use in vibration sensing due to their low noise and wide bandwidths. So it's clear to see that our medium performance sensors such as the ADXL 317 actually sit quite close to the limits of high performance sensors such as the ADXL 1002 and the ADCM-XL 3021. Next, we look at some customer pain points when trying to use MEMS sensors for CbM. For example, attaching MEMS sensors to assets and interfacing with existing piezo infrastructure. The ADXL 1002, as we just saw, is an industry-leading ultra-low noise and wide bandwidth MEMS accelerometer, and it's a viable alternative to piezo accelerometers. It's got comparable noise density, superior performance in temperature sensitivity, DC to low frequency response, and phase response. For customers who want to easily evaluate and replace piezo accelerometers with the 1002, we designed an interface that's compatible with IEPE, the de facto piezo sensor interface. Both of the sensor PCBs shown here are circuits from the lab reference designs, available on analog.com. The sensor interface PCBs were designed a little thicker than normal in order to maintain the daily sheet performance of the MEMS accelerometer. An extensive characterization was performed to ensure this. The reference design PCBs can be fitted to a piezo mechanical module and retrofitted and powered by existing piezo infrastructure. The aim with the IEPE and 4 to 20 mA reference designs was to make it very easy for designers to implement a MEMS sensor in place of a piezo sensor. But please note, analog devices do not make the piezo modules. However, a stud mountable cube is supplied with these reference designs to allow immediate testing out of the box. The mounting cube, along with PCBs and solder paste, etc., have been extensively characterized to ensure data sheet performance is maintained. And these solutions make it very easy for CbM designers to attach MEMS accelerometers to their assets, as well as seamlessly interfacing with existing piezo infrastructure. So this begs the question, should I use an analog or digital output accelerometer for predictive maintenance applications? We could see a range of accelerometers and their effective resolutions for use in CbM and PDM applications. But beyond 14-bit, the designer has to work with analog output sensors. Piezo sensors have dominated this space for decades, but recent advancements in MEMS technology, pioneered by analog devices, have enabled the ADXL 1002 family of MEMS accelerometers to now compete with piezo. So the options, if you want to work with the highest performance sensors, are to use an analog output sensor. So this means for CbM applications requiring the highest performance, the designer must consider the full precision analog data acquisition signal chain too. Here we can see another CbM reference design. Piezo accelerometers are a focus sensor for our precision signal chain. It's not all just about MEMS accelerometers. In this schematic we can see an IEPE piezo accelerometer signal chain example, and this is an optimal signal chain tested by analog devices to achieve the best performance. So we can provide current sources to power the piezo sensor, precision power to maintain stable low noise performance, wide bandwidth low noise amplifiers, ADC drivers to work with the atypical power supplies, as well as precision ADCs with wide enough bandwidth and speed and precision and filtering and so on to maintain the fidelity of critical information used to keep assets and even factories running. CbM system designers using piezo accelerometers require a high performance analog signal chain to maintain the fidelity of vibration data. The designers can now evaluate the signal chain performance out of the box simply by attaching their IEPE or ADXL 1002 IEPE sensor to the reference design. And we've put significant effort into validating this design to make the designer's life easier. Design files are also available where we highlight all of the parts used, and this will allow easier design into end solutions. We also have a host of other reference designs for space-constrained or compact designs, for multi-channel MEMS or piezo, for the lowest cost and for the lowest power. So if that's something of interest, please get in touch with myself, christopher.murphy@analog.com. We also have precision signal chain micromodules. We actually have a portfolio of these devices, and they combine various different technologies like programmable gain instrumentation amplifiers, ADCs and so on, switch mucks. And what's another key feature with these parts is our iPassive technology. Now remember, this all gets integrated into a system and package to deliver a more complete data conversion solution. But with our iPassives, we have highly matched, very precise passives that we can use around the signal chain, again to get even higher performance and take more of the design burden away from your customers. So micromodules simplify the task of developing high precision measurement solutions by transferring the design burden of component selection, optimization and layout. We take all that away from the designer and provide it all in the device. So these micromodule solutions can reduce system level development cycles, significantly reduce the PCB footprint. They can also reduce the cost of ownership associated with manufacturing yield and support, due to more of the signal chain being covered by just one datasheet. So let's look at some development platforms and solutions. Here we can see a range of CbM and PDM solutions from analog devices, ranging from sensors to machine learning enablement. So let's look at some of these in more detail. Analog devices' wireless CbM platforms highlight our low power, high performance signal chain, as well as our mechanical attachment capabilities that help to maintain wide bandwidth performance. For these wireless solutions, we have a single axis wide bandwidth or a triple axis narrow bandwidth offering. And these solutions come with complete signal chain for precision data acquisition, so sensors, ADCs, signal processing, transceivers, as well as software and GUIs for analyzing data. The mechanical design allows for either a stud or a magnetic mount to an asset, again for improved high frequency vibration performance. And this enables quick attachment while minimizing any packaging resonance. The wireless communications is based on Smart Mesh, which is a really robust wireless communication link that offers really low power. It's based on mesh networking. It provides wire-like reliability, time-stamped communication. Utilizing a CbM platform like this can accelerate time to market. All of the hardware and software design files are available for customization and development, and other sensors can be easily integrated. But it should be noted that this is a development platform for evaluation purposes. We have a Python-based GUI that's provided, again, as I mentioned, for data collection and for learning about your asset. Here we have a wired CbM reference design. On the left, we can see the ADXL 3021. And this contains 3 ADXL 1002s. It contains the ADCs, processor, memory, algorithms, FFT capability, all in a mechanical module with a resonance over 50 kHz. So any resonance that's possible is well away from the bandwidth of interest. And this highlights the capability of MEMS accelerometers to integrate intelligence at the sensor node, ensuring that the sensor is paired with the best signal chain and processing to achieve the best performance possible. On the right, we can see the reference design enabling robust wired CbM solutions, offering RS485 data and power over SPI. This solution can offer noise immunity across long cables up to 100 meters, whereby we can power the sensor from a master node. The several variations are available based on system requirements and solution cost. There's also potential to access an off-board low power processor for custom protocol and application design. And as you can see, there's a software tool that's provided that provides an easy to use environment to characterize and understand your asset's behavior. The machine learning kit is targeted at designers trying to understand their asset. So in the initial phase of developing CbM or PDM solutions. Typically, as a first step in developing machine learning algorithms, designers need to stream a lot of high quality data to their machine learning environment, whether that be MATLAB or Python or TensorFlow, etc., to understand the baseline of their asset. Next, fault and anomaly data are streamed to the machine learning environment where it will be characterized for comparison to the baseline. The machine learning kit enables this process out of the box. The accelerometer sensor data is output in the popular IEPE format, so designers looking to replace piezo sensors have an easy way to directly compare. The data acquisition board provides a full bandwidth data pipeline to the FPGA, where the system can monitor the data profile of the machine. There's an oscilloscope application that runs on the FPGA, so there's no PC required, just a monitor, that provides frequency spectrum information and allows users to quickly visualize their machine's health. Data can also be sent from the FPGA to the cloud. Python and MATLAB bindings enable designers to directly interface the machine learning data into these popular tools. Designers can then take their machine learning data and start creating algorithms for their equipment to better predict failures and maintenance strategies and potential factory downtimes. And again, for more information on any of the CbM solutions shown today, please contact me at this email address, christopher.murphy@analog.com. But to learn more, we have many articles on MEMS sensors, on CbM and PDM, on signal conditioning and vibration monitoring in general. And these are all available at analog.com/CbM. So we've got a host of new reference designs that have just released or will be releasing over the coming months. So Analog Devices have pioneered MEMS sensor developments and continue to do this by providing the only MEMS accelerometers that can compete with piezo accelerometers. We understand the design challenges of our customers and have created solutions to common pain points for MEMS use in CbM, such as mechanically attaching MEMS sensors to assets, replacing piezo with MEMS accelerometers. Analog Devices provide CbM and PDM solutions from sensors to development platforms that enable machine learning. For more information, please visit analog.com/CbM, and thank you very much for listening.